that if you are having a group of waves whose amplitude and phase are very close to each other, okay, they will travel with certain velocity. But then if you are basically having a single entity, you have got a one single wave, the velocity of that will be in fact faster than the speed of light. Okay, so this is something which we are going to check in our day-to-day life when we talk about waves. These are the waves which are actually traveling in bundles. Okay, it's not that we are having a single wave, we have a number of waves which are actually traveling in bundles. So in general, if I draw a curve of a wave, something like this, and we know that we can actually analyze that curve and find out a lot of information from there. So if we have a sinusoidal wave, or if we have a sine wave, is something like this, and if we just write down the phases, we know that this is the peak position, and if it's a sine wave, this value would be nothing but pi by 2, right? And here it would be pi, and so on. So each of these points in this particular wave corresponds to a phase. So maybe I want to find out what's the position here. Maybe this is A, and this particular point will give you some value of the angle, and that will actually correspond to a phase. If I consider a similar point on this side at the same height, and let's say this is B, then A and B both are in phase. Okay. On the other hand, if I consider any other point somewhere else, maybe C, you can say A and C are not in phase, or B and C are not in phase, and so on. Okay. So whether they are in phase or out of phase depends at what position the point is. Okay. So this is a wave, and at any point of time this wave is going to start traveling, and the time that it takes in traveling from this point to this point, okay, we can measure, okay, and we can check, do the calculations, and the velocity with which they travel from this point to this point when they are in phase, it's called the phase velocity. Okay, so in plain simple words. But then in reality we can actually have a group of waves, and they will travel with a different velocity altogether, and that is something which we call as the group velocity. Okay, so this is the preliminary idea, and let me just write down the words and sentences that you need. So phase velocity, so we'll start with phase velocity. So it's actually the rate at which the wave travels, so I will start with that. Rate at which the phase of a wave propagates. So now you understand what I'm saying here in space, right? So we know what is phase, and the rate at which it travels is called the phase velocity. So we can have an expression for this, we can do the numerical calculations, and let's do it. Okay, so we know velocity, okay, let me write it down as this, is equal to frequency into wavelength. We have already derived this in the last class, and we have seen how we have taken the basic relation of velocity is equal to distance by time. But we also know that any wave will be represented by a wave vector, which we write it down as k, and the relation between the wavelength and wave vector is 2 pi divided by lambda. So this is a relation which you might have done, okay, before also, and you should know that this is actually called a wave vector. Wave vector. So this is our wave vector. So that means I can find out what is my lambda. Lambda is equal to 2 pi divided by k. Right? Okay, so this is 2 pi divided by k. So that's important. Just a moment. second. Okay, so this lambda is equal to 2 pi divided by k, and what we can do is we can actually replace it here. Okay, so if we want to replace it here, what we can do is this. Therefore v is equal to n into lambda, which is nothing but 2 pi divided by k. Okay, so that means it is 2n pi divided by k, right? So that's there. So this is 2n pi divided by k. Okay, and what is 2n pi? Omega. So it implies that v, which is the phase velocity, is equal to omega divided by k. So this is the derivation for phase velocity in terms of frequency and wavelength, right? Because k is dependent on lambda, so this is actually in terms of wavelength. Okay, and in technically we call them as the wave vector, so frequency and wave vector, and this is the relation that we have. So this is the relation for phase velocity, or maybe we can say this is the velocity with which a phase of a particular wave travels. Okay, so this is phase velocity. Let's just have a look into group velocity now. Let's check group velocity. So let me just make the notes. Group velocity. So what happens is you can have n number of waves which is actually traveling, and all of these waves will have a very small difference in their phase. Okay, and they will superimpose. So if waves superimpose and then they are in phase, they're basically going to create an interference pattern. Okay, so what exactly you are going to observe is this. Okay, so what you observe is something like this, that if you add on all these wavelengths, okay, all these waves at different points, you are going to get a set of waves, and this will actually be something like this. Okay, something like this, and this will actually represent an envelope of waves. So you see, if you take this point, all these maximas, okay, and join them, this gives you an impression that this is actually a separate wave altogether, right? So if we just join them, okay, we are going to get this waves. So if we have a combination of waves, these waves will travel together, and this will be an envelope of wave. Okay, so this is an envelope of wave which does not have a single wave. We have all the waves which are traveling together. So imagine a number of speakers, okay, playing the music, and all these sounds that are coming out is in phase. Maybe it's the same music, it's the same tune, right? When it reaches your ear, you're going to hear an amplified signal. So the waves that is reaching your ear is actually a group of waves that is coming. So that envelope of wave is coming. So this is actually called the group velocity. What we need to understand here is that the velocity with which a single phase of wave travels, omega by k, is different from the velocity with which a group of wave will travel. Usually, the phase velocity is always greater than the group velocity. So we're going to see that mathematically. But then for group velocity, can we write down some sentences? Okay, so maybe I can just type. Okay, so let's write down what we can note for group velocity. So basically, when we talk about group velocity, okay, the group velocity of a wave is the velocity with which, okay, overall. So I hope you understand overall. That means the entire envelope here, envelope, okay, propagates through space. Propagates. So this is actually called the group velocity, and it's important. And I hope we understand what is meant by group. Maybe I can just put it inside bracket. So I can say what is wave group. Okay. So wave group means, you know, we have already studied about Young's double slit experiment and all, and you already know what do you mean by superposition. So if you have two waves, let's say y1 and y2, you can combine them and get the resultant. So y1 plus y2 will give you the resultant wave. But they cannot superimpose every time. They have to have certain conditions. For example, they should be very close in phase, okay, and they should interfere constructively, and there are conditions for constructive interference and so on. So this superposition of waves, okay, with wavelength. Okay, so the wavelength may be different, but then they have to have a constant phase difference or zero phase difference. Okay, and if we add them, the amplitude will also get added up. Okay, so that is very important. So what does it mean? It means that, okay, maybe one more line here. Yeah, amplitude and phase are of each wave, you can say, of each wave are such, okay, that they interfere constructively. That's very important, because if they don't interfere constructively, we're actually not talking about group velocity. We're actually talking about something which you call as noise. Okay, so that's very important. Constructively over a small region. So it's not that it might be, you know, interfering constructively for a very long period of time, then that has to be a perfect wave. It's very difficult to achieve that system. So constructively over small region of space, they will interfere constructively, and I will have this form of wave. And as soon as we go at the other end where we have got the nodes, we see that the intensity becomes zero. Okay, so this is important. So if we are talking about phase velocity and it has a relation like this, group velocity should also have a relation. But in group velocity, how many waves we are going to consider, that is going to be a difficult task. So what we do is, we're just going to consider two waves and find out what is their resultant velocity. Okay, and after that, you know, we can iterate this to a number of waves. Let's say n number of waves. We'll use mathematical tool of limits. Okay, so we're going to do that now. So let's try doing it. Okay, now the topic would be group velocity derivation. Okay, so we are going to derive the relation for group velocity. So the topic is group velocity derivation. So let's try deriving group velocity and see what we get. I'll tell you beforehand, group velocity that we are actually deriving, okay, you're going to get it in terms of omega and k as well. Okay, so for group velocity, first thing is we should have a wave and we should derive it, you know, we should represent it mathematically. So let's do it. So we have a traveling wave, and mathematically we know why. If you have a wave, you can represent it in as a cos function or sine function. So I'll take it as a cos kx minus omega t. So this particular expression has all the information about the wave, its amplitude, okay, its wavelength from k, what's its, you know, the frequency. If we want to know the time, we can also find out what's its position and so on, okay, at a particular point. So we have all the information about this wave, okay, and we can actually represent this traveling wave using this expression. This is something which you might have seen even in your lower classes. So lambda is equal to nothing but the wavelength. So when you write down in your exam, I would suggest that whenever you're writing down any mathematical expression, explain each and every term. That is very important. And omega is angular velocity, because physics is not pure maths, right? You cannot just write down expressions and don't explain anything. It will be a bit difficult. So you have to explain all the terms. A is amplitude. Okay, and if we look into this term, cos of kx minus omega t, I'm just revising, I think you already know it. It will actually define what is the shape of that particular wave, right? So if you have a cos function, I hope you remember, if you have a cos function, cos 0 is 1, so it will start from here and then it will go to 0 because cos 90 is 0 and then so on, right? But if you have a sine function, cos 0, sin 0 is 0, so it will start from here. Sin 90 is maximum 1, so it will go here, and then it will go like this, right? Something which you already know. So that means whether we are representing it by a cos function or a sine function will define what is the shape of that wave, right? So what we can say here is this will actually define the overall shape of wave. That's very important. So what we are going to do now is we are going to derive a relation for group velocity, and for that we are going to consider two waves. Okay, so let's do it. Let's consider two waves, okay, of equal amplitude traveling in positive direction. Okay, we're talking about direction is also important. Let's say positive x direction. I'm just writing it down in short. Okay, but then they have to have certain conditions with slightly, ज़्यादा नहीं, ठीक है, थोड़ा सा, slightly, a very small difference, okay, different, maybe wavelength should be very different, difference should be very small, and frequency, okay, and phase velocity. So in real life, having two waves from two different sources having perfectly the same velocity, same wavelength, same phase velocity is really difficult. So practically we can actually have two waves where the difference is very small, and because of that small difference, that's the reason that eventually as we go for a very long distance, okay, the group velocity property will get lost. So this group velocity property will remain intact for a short distance. Okay, so that's very important. So that's the theoretical idea. Even if you don't remember it, it's fine. For exam purpose, this is not needed, but then for understanding, this is important. Resultant amplitude. So we have got two waves, and we can actually find out the resultant amplitude, and I think these kind of problems we have done a number of times. Resultant amplitude would be nothing but y1 plus y2. Both these waves have got the values of wavelength and all, but they are slightly different, so they are not exactly the same. So I will take two different expressions. Their amplitude are same, okay, equal amplitude. So that means amplitude I can keep it as a cos. I'm saying slightly different wavelength, so that means k will change. So k would be 2 pi by lambda, that means it is 2 pi by lambda 1, so I'll write it down as k1. X is the position of the resultant, so it's fine. Minus the frequency will be slightly different, so I'll take it as omega 1 in time t. That's the first wave, plus second wave, amplitude remains the same, cos, this is k2x minus omega 2t. So what we have now here is a relation between cos plus cos. So if we all remember, we can actually use that relation, right? The relation that is there in trigonometry is cos A plus cos B. Let's recall this, 2 times cos of A minus B divided by 2 into cos of A plus B divided by 2. We remember this, so we can use this here. Okay, let's see what we get. So therefore I'll write down y as, so this is a, I can take it out common, there is a 2 in front here with the formula, so I can write it down as 2 times of a and then cos, okay. So this is k1x, k2x, so I can, so k1x, okay, I'll just do it here. You also do it on your own. A minus b, this is a, this is my in this case, okay, this formula. Okay, I won't write down A, otherwise you'll get confused. You'll thought this is the amplitude. Anyway, this is A and this is my B. So this is A minus B. So B is K2x. You do it and also keep checking mine if I'm doing any kind of mistake here in the writing, because it's going to be a longer derivation. This is there divided by 2. That's the first part, into cos A plus B. So divided by 2. So it is k1x minus omega 1t plus k2x minus omega 2t. Cos is an even function, so I hope all of you know cos of minus x is equal to cos of x. I'm going to use this also now, so I'm just writing this down beforehand. Times a cos, let's divide this thing by 2, and it is k1 minus k2. You can see it from here, it is k1 minus k2, but I will write it down as k2 minus k1 just to keep both the forms same. K2 minus k1, so that means I've taken one minus sign outside, into x minus, if I do, it will be again omega, omega 1 minus omega 2, or omega, you can see omega 2 is here, right? Omega 2 minus omega 1, so this is fine, right? So we can take this as omega 2 minus omega 1. So you can open it and check the expansion, and you will see that there will be a minus sign here. So cos of minus x is cos of x. It's an even function, so it will remain the same. So there is no change. Okay, so you can just do that trigonometry. I'm not explaining it right now. I think it's easy. Already given you the formula, and this one is something similar. Here we have got plus here, k1 plus k2. So maybe you can write it down as k1 plus k2 into x minus omega 2 plus omega 1, or omega 1 plus omega 2, same thing, to t. This is fine, right? Just add them up. Okay, take minus sign out, omega 2 plus omega 1. Okay, so this is the relation that we have right now. Now before we proceed, I'd like to tell you that we have already said that these wavelengths and the frequency are very close to each other. That means if I say k2 minus k1, k2 minus k1, that is nothing but a very small value, let's say delta k. So this is what we are going to represent it with. Similarly, omega 2 minus omega 1 is also a very small value. This is omega 2 minus omega 1. Okay, and please remember, these are small, both are small, right? It's obvious because they are very close to each other. But k2 minus k1 is the difference. That might be small, but k1 plus k2 might not be small, because that's not the difference. We are adding up two quantities, right? So I hope you understand this here. Let me just explain this before I write down the expression. Suppose your k1 is, I'm just taking a random value, 100 point, let's say it's 100, and k2 is 100.12341. So these two are very close to each other. So if I take k2 minus k1, this is going to be 0.12341. Very small, right? So this is delta k. But if I take k2 plus k1, this is definitely large, right? It is 100 plus 100, so it is 200. 200, okay? 0.0001. So I can take this is to be 200.000 or 01, which is almost equal to k1, twice of k1, is equal to twice of k1, right? So this is the assumptions that we are going to take here. So this is very small, so I've already written this as small, okay? But omega 2 plus omega 1 and k2 plus k1 are large, right? So you can see this example, we know that they are large. are large. Okay, so what we are going to do now is we are going to use this assumption in this expression, and let's see what we get. So therefore y is equal to 2 times of a cos of delta k into x, because k2 minus k1 is delta k, minus omega 2 minus omega 1 is delta omega into t divided by 2. So this is one, and the second one here is cos k1 plus k2. So I told you if I take k1 plus k2, k2 is very close to k1, so here we can approximate it to be twice of k1, right? So we can approximate it to be twice of k1. So what we can do is we can write it down as cos twice of k1 into x minus similarly twice of omega 1 into t divided by 2. Okay, it makes a lot of difference here. So you see this 2 and this 2 will actually get cancelled out if we take it common. So what I'm going to do is you can write down one more line, or you can also write it directly. I think it's quite obvious. So I will be just having this term, right? This is the term that we have finally. So these two are actually representing two different things here. These two are representing two different things. One is representing the envelope of wave. So here what we have assumed is k1 and k2 are very close to each other, so we can approximate that, and omega 1 is very close to omega 2, okay, because of which we are getting this relation. Done. What is this? This is the envelope that we have. Okay, this is the broad envelope. Okay, and this will actually control the velocity of the group of waves that we have. Okay, so what I'm going to do here is I'm going to explain these terms now. This is important. 2a cos of delta kx minus delta omega t divided by 2. This is actually called the broad envelope. If you look into this, you can analyze it, because if you look into this term, okay, just a bracket here, this term is actually representing a single wave. It is representing a phase of the wave, because if you talk about the expression that we started with which expression? We started with this. This is one single wave, right? So cos of k1x minus omega 1t will represent that. Mathematically we also arrive at the same result. This is going to represent that phase of the wave. So what is this going to represent? It has got the information about both the waves having k value as k1 k2, frequency as omega 1 omega 2. That means this is going to represent the envelope of the wave. Okay, so this is a broad envelope. Okay, and limiting, or maybe it will actually control the motion. So I can write it down as limiting or modulating a high frequency wave. A high frequency wave. And what is that high frequency wave? This wave. This wave is controlled by this, because this is actually a term which are connected. We cannot ignore this when we are analyzing this wave, right? So high frequency wave, कौन सा है मेरा high frequency wave? Cos of k1x minus omega 1t. Mathematically, when we analyzed, we saw that this envelope and this phase of a wave is actually connected. Okay, so if I consider the the velocity of this entire wave, it has to be different from the velocity of this, because by definition velocity is equal to omega by k. So what is my value here? It is omega by k here. So that's the wave with which this travels. but this is actually the envelope of wave or the group wave. Here it's not omega, it is delta omega. It is not k, it is delta k. So this would be delta omega divided by delta k, and that's the relation for group velocity. Okay, so what we can say is, so envelope, that means the group of waves, and wave, the wave that we are considering here, the phase velocity, has different velocities. Okay, this is very important to understand. So generally when we write it down, I think we have already done it at the beginning of the class. V velocity is equal to omega divided by k. So this is your phase velocity. But if you look into the group of waves, okay, it is actually defined by this expression. Okay, so maybe we can write it here. Okay, group velocity. So we are almost towards the derivation part, ending it. Group velocity described okay, by, which is describing the group velocity, this result, right? 2a cos delta kx minus delta omega t divided by 2. This is your describing the group. Okay, so here we can say v, and I will just differentiate it from phase velocity. So I'll write down a g, the as a subscript. I will find this notation in most of the books, is equal to delta omega and not omega divided by delta k and not k. This is your group velocity. So this is a result when we are considering only two waves. Okay, so what happens when we are adding many waves? Therefore, when many waves are added, we know delta k is very small, right? Delta k is small when we are adding them up and all of them are very close to each other. We are adding one with the other and then with the other. This delta k will keep on reducing. So it will actually, it will be a limiting condition. So therefore we can say Vg is equal to limit delta k tends to 0, right? So maybe you have got two waves which are very close to each other. You get one value of delta k from there, and then you get another two waves, which is this. Let's say you are getting another delta k from there, so that's a delta k2, and then they are combined to form a group. Many waves are combining, right? They are again combining to form a group, so the resultant may be another delta k. This will be even smaller. This will be even smaller than this. So if we are taking a number of waves together, this will become so small that it will be limited to 0. So limiting to 0. It's not 0, it tends to 0. I think limits and continuity you might have studied in your 11, 12 maths. Or delta omega divided by delta k. And what is this? This is the definition of differentiation. So that means this is d omega divided by dk. That is the group velocity. Therefore, Vg, which is the group velocity, is d omega divided by dk. That's the derivation for group velocity. Very important. So you might get some questions in your exam, numericals and all. Maybe the form of frequency would be provided to you, and then you can just differentiate it with respect to k and find out what is the group velocity. Okay. So the bottom line is that group velocity and phase velocity are two different phenomena. Okay, the velocity with which a phase of a wave travels is omega by k is different from the velocity with which a group of wave will travel, which is d omega divided by k or dk. So practically it is seen that the phase velocity is very high compared to a group of waves when they are traveling together. So if you are considering a group of wave, you will get this envelope, and within these waves are also traveling, these waves. So the velocity with which this wave is traveling will be more compared to the velocity with which this entire group is traveling. Okay, and this is traveling within this system. Okay, so there are certain animations on YouTube which you can check. Okay, and then you'll clearly understand this. Okay, but anyway, I don't have the video right now, so I'll show it to you. So there is something which is very interesting here. Okay, I'll just show something more, which is again important, and this may be an objective question. So how much mark for this particular question? Maybe I can tell you this. So you see, it's not a short derivation, and if you are explaining it properly, this is actually you can say the answer which is complete in every sense. I've written everything here, so you can write down this answer and then you can get your full mark. So maybe it will be around 3 to 4 marks or 5 marks. Okay, so try to derive it properly and also explain. Don't just keep deriving it at the end. Somewhere you'll write it down as Vg is equal to delta omega by delta k, which is equal to d omega dk. That is wrong. That is totally wrong mathematically. Delta omega by delta k is not equal to d omega by dk. There has to be a limiting condition. So if you go by the definition of differentiation, if this delta k, which is discrete, okay, goes to 0 or tends to 0, and then only we can say it's d omega by dk. So use those mathematical tools and write down these answers correctly.